Okay, short lecture today, the time we have remaining. And it's an appropriately short topic, but let's see how far we can go with the example. So, source transformation. All right. So we looked at Thevenin and Norton circuits. We looked at a few examples. We'll on Friday and then Monday and Wednesday, we'll look at a few more examples in class for the entire quarter. So we're almost at the end. We have completed almost all topics. So we spoke about this earlier, how the Thevenin and Norton circuits are equivalent to a large circuit. And because they're equivalent, we can say that the Norton and Thevenin circuits are also equivalent of each other. And from there, we can extend that to a concept known as source transformation. Source transformation essentially says, if you have a voltage source in a circuit, you can convert it into a current source or model it as a current source and vice versa. The voltage source must be in series with the resistor, and the current source would be in parallel with that same resistor. Okay. This requires that we disconnect a source from the circuit, which would leave behind two open terminals. And then between those exact same terminals, we can connect a current source and voltage source as vice versa. So just to let you know, this is not a technique that I personally prefer. I try to avoid it as much as possible, is because it's a little tricky to determine where the source is actually connected, and to disconnect it from a circuit, transform it, and then plug it back into it. Okay, so it gets a little bit tricky. And so I tend to make errors on using this technique. Anyway, here's an example. So we have a circuit. Circuit has a voltage source on the left and a current source on the right. The voltage source has a resistor in series with it, and the current source has a resistor in parallel. Real life circuits tend not to be this kind and this straightforward. Okay, it's always going to be very tricky. But let's say how we can transform the source and solve for the voltage and current in there. Okay, so this is the original circuit. The original circuit is marked with having current I1 and I2 as flowing through those two resistors. So if we wish to find the value of these currents, we can use any of the techniques that we have learned so far. We can use node voltage, mesh current, we can use superposition. Superposition would by far be the simplest and the straightforward, because it only has two resistors. But if you're doing source transformation, then this is what we need to do. We are going to break the circuit into two parts. The one on the left is the voltage source with a series resistor. And the one on the right is going to be the current source with the parallel resistor. Okay. A 1 amp source, R2 of 10 ohms. Now, when we break this, we'll keep the terminals still the same. Okay. And we are only going to transform the right side. Actually, I just want to show how we can transform both sides. So if we transform the circuit on the left, which is the voltage source, it must have a resistor in series with it between those two terminals. Okay. Which obviously, this circuit being very convenient for us, already has a resistor in series. Okay. So if we transform the left and the right side, the left side can be transformed as a current source. It could become a current source in parallel with a 5 ohm resistor. The value of that current source can be given from Ohm's law. So the voltage source is 20 volts, R1 is 5, current I is V over R, so 4 amps. And 4 amps going from minus to plus, source always gives The source current always flows from minus to plus. So this would flow in the upwards direction. And then the terminals remain the same, A and B. Okay, yes. So the concept comes from Thevenin and Norton equivalent circuits. As Thevenin and Norton are the same equivalent to the same circuit. And so we can say resistor in series, the Thevenin equivalent is the same as the current source in parallel with the same resistor, which is the Norton equivalent. Okay. Does everybody understand? Essentially, what we are doing is we are taking a voltage source in series, let's say it's a Thevenin equivalent, and replacing it with this Norton equivalent. And on the right, we can do the same. We have the Norton equivalent, meaning a current source in parallel with a resistor, and we can replace it with a voltage source in series with that same resistor. The outer terminals must remain the same. They cannot change. If the current is going upwards, then the arrowhead is plus and the tail is minus. And so for this voltage source, answer is 10 volts, plus at the top, minus at the bottom. And that's how we can transform a voltage source and a current source into each other. Let's take a pause before we go into the analysis in figure B and figure C. Do the transforms make sense? Any questions? Okay. All right. So let's see then how we can actually determine the value for I1 when we transform just the right side of the circuit into a voltage source. Okay. If we do that, we try to solve for this, what do we notice? We now have two voltage sources, 20 volt on the left, 10 volts on the right. So then what is this is 20 volts and this is 10 volts. What is the voltage applied to those resistors? $110. I got one answer. 30. Well, difference because it's not minus 10. If it was minus 10, it would be 30. But in this case, because they're both positive, it'll be 20 minus 10. And so this is 5, this is 10. We can also apply KVL to determine the actual voltage. But we 20 minus 10, and so we're applying 10 volts. And because we are applying 10 volts, we can calculate the current by simple Ohm's law. So instead of doing node voltage analysis or mesh current analysis, we can simply apply KVL and then Ohm's law and determine the direct answer. And so it becomes a two-step answer versus writing like multiple equations. So total voltage will be 10 volts. And then ten over 15. which should be about what, 6 point something. 0.6667. What do you all think? 0.667. So again, you have two sources in the circuit, but source transformation makes it easier. Now, if you notice, I1 is still the current flowing through the 5 ohm resistor, but this current is not the same as I2. Okay, because we transform the right side, that current is not the same as I2. So the answer for I1 is correct, but I2 is yet to be determined. And so we can transform the left side into a current source. And obtain this circuit. If the 5 and the 10 ohm resistor was one single resistance, which of course they are in parallel, what is the total current going into that resistance? We can apply KCL. The total current would be 4 plus 1, 5 amps going in. And if 5 amps are going in, we can apply current division to directly determine the current flowing through the 10 ohm resistor. So I2 in this case would be a fraction of 5. We need to find REQ. REQ of 10 and 15 would be 50 divided by 15. So 50 divided by 15 is 3.33 divided by 10. And therefore, I2 is equal to 5, 1.6667 amps. You can try and solve this. Not try, I would strongly recommend. Use node voltage analysis, mesh current analysis, and superposition. And see if you obtain the same answers. Okay. Again, the source transformation would change the circuit. What technique you apply after that, it depends on the circuit. Okay. In this case, the circuit is rather straightforward. It's simple, so it makes sense to use source transformation. But for the most part, I try to avoid that technique. I try to avoid it. Okay. All right. We are almost out of time. Any questions? Okay. We'll end class here today. We'll pick up here again on Friday. Look at a few more examples. Then we'll get into, well, just problem solving until the end. We have almost wrapped up. So we'll finish up like Monday and Wednesday. And then Friday pretty much should be like a pre-study day. Oh, there will be, I can't recall if I posted a homework, but there will be one more homework for next week. Thevenin and Norton, kind of important topic. Yes, Thevenin and Norton. But that will be mostly setup, not analysis. Oh, almost getting there. I'm almost getting there, yes.